Good morning and welcome to the Inverse Laplace Transform primer. This is a basic of Inverse Laplace Transform and some methods to find Inverse Laplace Transform. In this session we will discuss a definition of Inverse Laplace Transform, basic methods, revision of partial fraction technique in view of Inverse Laplace Transform, and use of partial fraction technique in finding inverse Laplace transform. First of all, we formally define what is inverse Laplace transform. We are familiar with the definition of Laplace transform. L of f of t is equal to f bar of s. Inverse means we start our journey from f bar of s and come back to f of t, or simply we start from s domain and come back to time domain. So formally it is defined as L inverse of f bar of s is equal to f of t. So f bar of s is our argument. Then we take L inverse, we come back to time domain. That means the variable is now changed to time domain variable t. For example, we consider this L of sin a t. L of sin a t is equal to a by s square plus a square. So when we take L to the right side, it becomes L inverse of a by s square plus a square equal to sin a t, like this. One more step, we can take the constant a outside. So a into L inverse of 1 by s square plus a square equal to sin a t. Or we can bring this a in the denominator on RHS. We got a general formula, that is L inverse of 1 by s square plus a square equal to sin a t by a, like that. In this way we can formulate the standard results for inverse Laplace transform. L inverse of 1 by s equal to 1, L inverse of 1 by s minus a equal to e raised to at. First of all, you should learn the formula Laplace transform of e raised to at equal to 1 by s minus a. Then you think reverse manner. L inverse of 1 by s minus a equal to e raised to at. L inverse of 1 by s raised to n plus 1 equal to t raised to n by n factorial. L inverse of 1 by s minus a the whole raised to n plus 1 equal to e raised to at into t raised to n by n factorial. Here note that this s changes to s minus a in s domain. That means shifting happened in time domain. This shifting is actually the effect of multiplication by e raised to at. So this shifting s to s minus a is in effect multiplication by e raised to t. So when we put e raised to at in the right side, this a will be disappeared. So 1 by s raised to n plus 1. L inverse of 1 by s raised to n plus 1 is t raised to n by n factorial. That is the second part. That means first we take the shifting part and its effect is e raised to at. Now you just hide this a. Remaining portion is 1 by s raised to n plus 1. Take L inverse, that is t raised to n by n factorial, like that. In this way we can write all the formula for L inverse of 1 by s square plus a square as 1 by a sin a t. L inverse of s by s square plus a square equal to cos a t. L inverse of 1 by s square minus a square equal to 1 by a sin h a t. L inverse of s by s square minus a square equal to cos h a t. L inverse of shifting by b, L minus b by s minus b the whole square plus a square equal to shifting in terms of b, so e raised to bt into cos a t. Then L inverse of 1 by s minus b the whole square plus a square equal to 1 by a e raised to bt sin a t. L inverse of shifting s minus b by s minus b the whole square minus a square. Here we have minus, so cos h, e raised to bt into cos h a t, like that. Then fourth and fifth equations, L inverse of f bar of s by s is equal to integral 0 to t f of tau d tau. First you should realize Laplace transform of integral equal to division by s. So inverse of division by s is integral of f of t dt. Similarly, Laplace transform product with t is equal to derivative. So L inverse of derivative is equal to minus product with f of t, minus t into f of t. Then different methods to find inverse Laplace transform. The most popular and useful approaches are, first one is direct method. That means we make use of the direct results that we have seen in the last two slides. Then method of partial fraction. This method is familiar to you during your plus 2 classes, because we have used partial fraction to calculate integration. Then using properties of Laplace transform, like Laplace transform of multiplication by t is derivative, so inverse Laplace transform derivative is multiplication by t, like that. Then method of convolution. These four popular methods will be discussed in our coming sessions. Our aim is to find inverse Laplace transform functions. First of all, we will discuss the direct method. Direct method is straightforward. We try to associate given function S domain into the Laplace transform of basic functions. For example, consider the function s plus 3 by s square plus 9. Suppose we want to find inverse Laplace transform. First of all, we try to write this expression into two simple fractions. That is, denominator contains two terms and denominator is a s square plus 9 function. So divide each term in the numerator by s square plus 9. So we got answer like this: L inverse of s plus 3 by s square plus 9, because we need inverse Laplace transform. We split it into small fraction, s divided by s square plus 9 plus 3 divided by s square plus 9. That's all. We apply term by term division. Now apply L inverse. L inverse is again a linear operator. So L inverse of the first function plus L inverse of the second function. From the direct result, we know L inverse of s by s square plus a square equal to cos at. Here in the place of we have 3, so cos 3t. Similarly, L inverse of a divided by s square plus a square is equal to sin at. Here a is equal to 3 and therefore sin 3t. So L inverse of s plus 3 by s square plus 9 is equal to cos 3t plus sin 3t. We simply use the direct results of inverse Laplace transform. Here the denominator is exactly of the form s square plus a square. So the procedure is very simple. Now we consider more complicated problem. So problem is like this: find inverse Laplace transform of 3s minus 137 divided by s square plus 2s plus 401. See, note that we can apply term by term division, but the denominator is not a perfect square. So we try to make the denominator as a perfect square, then apply term by term division, then apply the standard results in L inverse. So we start from our s function 3s minus 137 divided by s square plus 2s plus 401. First of all, we complete the square in denominator. That means we take half of the coefficient of s, square it, and add and subtract to the denominator. Or in single words, we simply add and subtract square of half of coefficient of s. We add and subtract squares of half of coefficient of s. So s square plus 2s plus 1, adding that square of half of coefficient of s, then subtract that square of half of coefficient of s, that is minus 1. Then we put it together, it is s plus 1 whole square. Then 401 minus 1 is 400. 400 is 20 square. So we can complete the square in the denominator. Now we apply term by term division. Before that, in the denominator we have s plus 1 whole square. So that means we are going to change every s into s plus 1 form. So we replace the numerator s by s plus 1. So 3s plus 3. This 3s plus 3 minus 140 gives 137. We should keep in mind that this rearrangement or manipulation will not change the values in the numerator and denominator. So this is a mathematical manipulation. Now we apply term by term division. 3 into s plus 1 divided by this denominator minus 140 into 1 by this denominator. Now these terms are familiar to us. L inverse of this expression, we know the standard result. L inverse of this fraction, we know the standard result. So apply L inverse on both sides. The left side is actually 3s minus 137 by s square plus 2s plus 401. L inverse of 3s minus 137 by s square plus 2s plus 401 equal to, we apply linearity property. Take these 3 outside. L inverse of first fraction, s plus 1 by s plus 1 whole square plus 20 square, minus constant 140 into L inverse of second fraction, that is L inverse of 1 by s plus 1 whole square plus 20 square. Now there is a shifting happened, s changes to s plus 1. That means in time domain we have to multiply by e raised to minus t. When we multiply by e raised to minus t, this 1 will disappear. So s by s square plus 20 square, that is cos 20t. Then put this minus 140 constant. This is L inverse of 1 by s square plus a square, that is 1 by a into sin 80. Here a is 20, so 1 by 20 into, but there is a shifting happened. So multiplication by e raised to 80 there, here a is equal to minus 1, so e raised to minus t. Then there is only 1 by s square plus a square, that is 1 by a. I put 1 by a, 1 by 20 here. 1 by s square plus a square is sin 20t. sin 20t. So final answer is 3 into e raised to minus t into cos 20t minus 7 e raised to minus t into sin 20t. In this problem, there is only one additional step, that is completing the square in the denominator. Then we make use of our observation. S is replaced by s plus 1 only if the shifting happened. That will be there in every s. Wherever s, you should replace it by s plus 1. We apply that method, simplify it into smaller fraction, apply L inverse, and we got the result. The next is method of partial fraction. This partial fraction method is a mathematical approach that try to express a given proper fraction into sum of simple fractions. That's all. We divide or we split a proper fraction into sum of simple fraction. So in view of Laplace transform, what we are going to do? In this approach, we divide the given proper fraction in s, that is in transform domain we have s is the variable, into partial fractions. Then apply basic results to that partial fraction and apply linearity property to get the inverse Laplace transform of original problem. For example, consider this problem. Find L inverse of 1 by s plus 4 into s plus 16. See, this is a proper fraction. Proper fraction means the power of s in the numerator must be less than power of s in the denominator. That means further division is not possible, or it is in irreducible form. Here in this problem, numerator is a constant. That means s raised to 0 is there, 1 into s raised to 0. So degree of the numerator is 0. And again, degree of the denominator is the degree of the leading term, that is s square here. S into s square is the leading term, so 2. That means degree of numerator is less than degree of the denominator. So it's a proper fraction. First step is we take this fraction and split into small sub fractions and then apply L inverse. See, 1 by s plus 4 into s plus 16 can be written as a by s plus 4 plus b by s plus 16. This representation is called partial fraction representation. Then we multiply this left side denominator s plus 4 into s plus 16. We take this s plus 4 into x plus 16 and multiply both sides. So left side becomes 1. Here it becomes a into s plus 16 plus b into s plus 4. That's all. We multiply both sides of this expression with the denominator of LHS. The next step is eliminating variables. To find b, I first eliminate a. How to eliminate a? The idea is very simple. We replace this s by minus 16, or put s equal to minus 16. So minus 16 plus 16 0. So a will be eliminated. Minus 16 plus 4 is equal to minus 12. So minus 12 b is equal to 1, or b is equal to 1 by minus 12. Similarly, to find a, I eliminate b. For that I put s is equal to minus 4. So this term will be 0. So minus 4 plus 16 is 12. 12a is equal to 1. So a is equal to 1 by 12. Now we substitute a and b here. So 1 by s plus a and s plus 16 is equal to a. A is 1 by 12. 1 by 12 into 1 by s plus 4 plus b is minus 1 by 12. Minus 1 by 12 into 1 by s plus 16. That is next step. But here the magnitude is 1 by 12. We can take 1 by 12 outside. So L inverse of 1 by s plus a into s plus 6, that is left side, equal to, I take this 1 by 12 outside, then remaining term in the numerator is 1. 1 divided by s plus 4. L inverse of 1 by s plus 4. Then there is a negative for b. So minus is here. L inverse of 1 by x plus 16, because this 1 by 12 is taken outside. But we are familiar with the result. L inverse of 1 by s plus 4 is equal to e raised to minus 4t. Then we put this minus here. L inverse of 1 by s plus 16 is equal to e raised to minus 16t. So we got L inverse of 1 by s plus 4 into s plus 16 equal to 1 by 12 into e raised to minus 4t minus e raised to minus 16t. Or in a sense, we express a proper fraction in terms of simple fractions using partial fraction method, apply L inverse. That's all. There is nothing new. We use the basic results of L inverse and also apply some partial fraction techniques or completing square techniques to simplify our rational expression into familiar form to apply L inverse results. Then inverse functions with special form. Suppose we want to find inverse Laplace transform of some special form functions like logarithm, tan inverse, or cot inverse, etc. In the previous slides we have seen that we apply Laplace transform on algebraic functions, more clearly rational functions. In some cases there are no rational functions, it will come in the form logarithm of s function, tan inverse of s function, cot inverse of function, etc. In that case we will use this result. If our function f bar of s is of the form ln tan inverse or cot inverse, then if we put it as f bar of s, then find f bar dash of s. Then L inverse of f bar dash of s equal to minus t into f of t. That is the result we obtain from this step. L of t into f of t, L of multiplication by t is derivative of f bar of s. This derivative is denoted by f bar dash, and there is a minus. So f bar dash of s is equal to, here f bar dash of s is equal to minus of L of t into f of t. Now we need L inverse. So we put this L into the right side. So t into f of t is equal to L inverse of f bar of s into minus 1. Or simply minus t into f of t is equal to L inverse of f bar dash of s. From this step we can calculate f of t. To get f of t, you put this minus t into the left side. That is L inverse of f bar dash of s by minus t. Or in a straight way, we calculate f bar dash of s and find L inverse. Then use this result. That's all. As a simple problem, find L inverse of logarithm of s plus a by s minus a. Now look into this expression. It is a log function. So special form. So we have to apply that special method. The first step is we expand log a by b as log a minus log b. We represent it as f bar of s because it's a s function. Now find f bar dash, its derivative. Then apply L inverse and apply results. Okay. This is in the special form, so we will use the result L inverse of f bar dash of s equal to minus t into f of t. So we have to find f bar dash of s. We write f bar of s like this: ln of s plus a by s minus a equal to, it is of the form ln of a by b, ln of s plus a minus ln of s minus a. It is f bar of s. Now find f bar dash of s because I need this f bar dash of s. Derivative of logarithm is 1 by s plus a. Again minus, we put minus here. Derivative of log s minus a is 1 by s minus a. Derivative of logarithm is 1 by that argument. So we got this. Now we apply this result. Therefore L inverse of f bar dash of s, apply L inverse on left side. We do the on right side. L inverse of 1 by s plus a. L inverse of 1 by s plus a is e raised to minus at. Put this minus. L inverse of 1 by s minus a is e raised to at. But as per this result, this expression equal to minus t into f of t. We need f of t. So we have to divide the left side by minus t. So to divide this minus t, we multiply the numerator by negative. So this minus become positive, this plus becomes minus. So f of t, this f of t is equal to e raised to at minus e raised to minus at by t. So Laplace transform with this of this log function become a division by t expression. As a final step, we are going to simplify this e raised to at minus e raised to minus at. We have already known sin h at is equal to e raised to at minus e raised to minus at by 2. In the numerator we have e raised to at minus e raised to minus at. So substitute e raised to at minus e raised to minus at by 2 into sin h at. So we call this simple expression. So L inverse of log form becomes 2 sin h at by t. In the case of cot inverse, in the case of tan inverse, we will do the same procedure. First of all, we write the given s function as f bar of s. If it is log, cot inverse or tan inverse, find out f bar dash of s, then apply L inverse, we got the result. So the important takeaways: basic results to find inverse Laplace transform. There is nothing new. We have already familiar with Laplace transform results, then we take the inverse. That's all. We have to learn about type of results. Okay. Then methods to find inverse Laplace transform. There are 4 popular methods. One is direct method, second one is by method of partial fraction, third method is applying some special functions, special properties of Laplace transform, and finally convolution. Except the 5th method, I have discussed all the first 2 and 3 methods here. We will discuss more problems in the next section and also the convolution property and convolution theorem. So thank you very much for the patient listening, and you have to complete this primer lesson before next interactive session. Thank you very much.